Welcome to Homework Lib.
Hi, so over here we just need to find the different components that we have on this vector. Here I'm going to try to replicate the drawing that you have here. This is minus y. And we know that the vector has a projection that goes into the xy plane and has an angle over here equal to 45 degrees. And at the same time, the angle that the vector makes with respect to the plane, this angle over here, corresponds to 60 degrees. So effectively we have two different triangles. With one of them we can know what is the projection over the set component and what is going to be the longitude of this vector over here. And finally, with this longitude, we're going to use that new triangle in order to get the x and y components. Okay? So, first of all, let's focus on, I'm going to redraw this. Let's think about this triangle with 60 degrees. This is our vector. Let's call this vector f. And let's call this line over here, this is equivalent to this red line. This is going to be the projection of f on the xy plane, right? And what else do we have? Well, we can know directly f on the set plane. So just to draw it a little bit better, let me redraw the force f like this, in black, of course, black. Okay, so this is going to be our force F equal to 100 newtons and this angle of 60 degrees Celsius. And this would be our set component of F. So how can we find the value for F set? Well, we can use trigonometric functions. In this case, sine of 60 degrees. It is going to be equal to the opposite divided by the hypotenuse. So it's going to be F set divided by F. So the component in the z direction is equal to 100 times sine of 60. That is going to be equal to 86.6. This is just the magnitude of that axis. Now, if we compare this to the drawing over here, we know that this is in the positive z direction, right? So the z component, it is going to be equal to 86.6 in the k direction. So now what we need to know is the size of the xy component. And that xy component, that component in that plane, is going to be equal to the force times cosine of 60, which is exactly 50. Okay. Now to be clear, that 50 corresponds to the magnitude of this line that we have, the one that is in between the xy plane. Okay. Well, x minus y plane if we're hyper precise. So now let's redraw this new line in order to get the x and y components. Here we have the x direction, over here we have the minus y direction, and we have a vector that has a magnitude of 50 newtons. And we know that the angle over here is 45 degrees Celsius. So this new drawing is the same as if I were saying that I am looking at the original picture from above, from the positive z axis. So we can get the x component, same thing, we're going to use trigonometric functions. In this case, the x component, we want something that goes into the adjacent catet over here of our angle. So that is the value for fxy, the component that we just got, times the cosine, in this case, of 45 degrees. And finally, this is 50 times cosine of 45 degrees. And the component in minus y, recall that this is the minus that we have here, it is going to be equal to 50 times sine of 45 degrees. The results that we get are 35.35, well, 355, that rounds up to 35.4. The same thing here on the minus y direction. Remember here, let's emphasize that this is the minus y direction. And with this, we can finally get the different components of our vector. In the x part, x is positive as the axis is defined. So we have 35.4 in the I direction. In the y-axis, we have a negative over here. We're going to project into the negative y-axis. So this is going to be minus 35.4 in the j direction. And finally, we simply are going to add the z component, that is 86.6 in the k direction. And that would be all. This would be equal to the vector f that we were provided at the beginning.